In Chapter 9, we're going to be talking about thermochemistry. So first, let's go over some definitions. First of all, what is thermochemistry? Thermo means heat, so thermochemistry is the chemistry associated with heat. So we're trying to find the amount of heat that's absorbed or released, and it could be during either chemical changes or physical changes. So energy is the capacity to supply heat or do work. We're going to look at an equation a little bit later in this chapter that has heat and work as variables in it. And both of those are just different forms of energy. There are two main types of energy, potential energy and kinetic energy. Potential energy is the energy that an object has based on its position, composition, or condition. Basically, where it is, what it is made up of, or what are the circumstances surrounding it. So an example is a ball poised at the top of a hill. It's ready to roll down. And based on the fact that it's at the top of the hill, it has some potential energy. Kinetic energy is energy related to motion. So when the ball is rolling down the hill, that is involving kinetic energy. So we're going to use a law called the law of conservation of energy, which says that energy can't be created or destroyed, it can only change in form. So it could change between kinetic and potential, or there are a variety of other types of changes it could also undergo. So for example, we could push the ball to the top of the hill, and by doing that, we change kinetic energy into potential energy. Or we could push the ball down the hill, which would turn potential energy into kinetic energy. Let's talk about some related concepts as well. So thermal energy is a particular type of kinetic energy. And it's one that we're going to be talking about a lot in this chapter because it has to do with the kinetic energy, the energy of motion associated with atoms and molecules. So atoms and molecules are constantly moving around. They're sort of jiggling in space all of the time. They're vibrating. And so they have a thermal energy associated with them because of it. Temperature is a related term, but it's not exactly the same thing. Temperature is a quantitative measure of hot or cold. We have a number associated with it we can measure on the thermometer. And it's going to be directly proportional to the thermal energy. So the higher the thermal energy, the higher the temperature, and vice versa. So in the picture, you can see the hot water has a lot of lines around each of the balls. That indicates that it's moving more. So it has a higher thermal energy. And in terms of temperature, we would measure it and say that it's hot. For the cold water, it has fewer lines around it, indicating that it's jiggling less. There's less kinetic energy associated with it. So thermal energy is lower. And also, when we measure its temperature, we find that it's cold. Another related, but not exactly the same term is heat. So heat has the variable Q, lowercase q, and it's going to be the transfer of thermal energy between two bodies at different temperatures. So the heat is always going to flow from the hotter substance to the colder substance. That is the substance that has the higher thermal energy to the substance that has the lower thermal energy. So you can see that in the pictures down at the bottom of the screen. The higher thermal energy substance is the one with the red that has lots of lines around it, and it's designated H for hot. And then there's the blue lower temperature substance that has lower thermal energy. So the heat is flowing from the hot to the cold. And as it does that, the hot substance gets cooler and the cool substance gets warmer. And the heat continues to flow until they both reach the same temperature as each other, which we call the equilibrium temperature. Now, heat can still flow in between the two substances, but it's going to sort of flow back and forth at the same rate, if you will. So there's no net change in heat once it reaches that equilibrium temperature. So both physical and chemical processes can absorb or release heat. When a change releases heat, it's called an exothermic process. Exo means out and therm refers to heat. So heat is going out in an exothermic process. A reaction or change that absorbs heat is an endothermic process. Endo means in, and therm, again, is heat. So endothermic means heat is going in. So an example on the left, we see an exothermic process where a lot of energy is coming out of the reaction. In a cold pack, that's going to be an endothermic process. Heat goes out of your body and into the cold pack. So since heat is going into the cold pack, it's endothermic based on the cold pack. So let's go over some units of energy. One common unit of energy is the calorie, abbreviated little c-a-l. And its definition is that it's the amount of energy required to raise 1 gram of water by 1 degree Celsius. And remember, Celsius and Kelvin have the same size of a degree. So a change of 1 degree Celsius would be the same as a change of 1 degree Kelvin. Now, the calories that you actually see on your cereal boxes or macaroni and cheese, those are actually going to be big C calories. So big C calories are equal to 1,000 little c calories. In other words, they're the same thing as a kilocalorie, or kcal for short. Another common unit of energy is the joule. A joule is the amount of energy needed to move a 2 kilogram mass, like the medicine ball in the picture, with a velocity of 1 meter per second. So a joule is going to be equal to 1 kilogram meter squared per second squared. So you'll see those two sets of units used interchangeably. It depends on whether we want to focus on joules or whether we are dealing with things like masses and velocities, in which case we might end up with units like kilogram meter squared per second squared. The relationship between calories and joules is that 1 little c calorie is equal to 4.184 joules. So a joule is about 4 times as big as a little c calorie. So we can measure the properties of substances related to heat. And one property is called heat capacity. Heat capacity has the abbreviation capital C. We have a lot of different units here that have a C in them, or they start with a C, so please try not to get them confused. So little cal is calories, capital Cal is kilocalories, or big C calories. Just a plain old C that's capital is going to be heat capacity. And then we'll talk on our next slide about one with a lowercase c, which is specific heat. Additionally, there's the degrees Celsius, which is also a C. So if it has the degree symbol next to it, it's a unit of temperature, which is Celsius. If it does not have the degree symbol next to it, then it's capital C, heat capacity. And heat capacity is defined as the amount of heat that a body of matter absorbs or releases when it experiences a temperature change, in other words, delta T, of 1 degree Celsius. Delta is the symbol that we use for change. So delta T is change in temperature. And remember, heat, we use Q as its symbol. So we can write this in equation form. Capital C, heat capacity, equals Q over delta T. Q is quantity of heat divided by delta T, change in temperature. And by the way, that's why we use the symbol Q, is it's short for quantity. So we could have two different pans, and we heat them up with a temperature change of 50 degrees Celsius. So let's say it started out at 25 Celsius and went up to 75 Celsius. 75 minus 25 equals 50-degree temperature change. So let's say we heated it up by 50 degrees and measured the amount of energy needed to do that. For our small pan, it only needed 18,140 joules to make that temperature change for that pan. For the large pan, it needed 90,700 joules for that same temperature change. And that is because the larger pan is larger. There's more mass for it to heat up. So the heat capacity of the small pan is 363 joules per degree Celsius, whereas for the large pan, it's going to be 1,814 joules per degree Celsius. So the small pan has a smaller heat capacity, and the larger pan has a larger heat capacity. Think of it as the ability to hold heat or store heat. The larger pan can store more heat. Specific heat, on the other hand, we represent with a small c, and it's going to be the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. For heat capacity, we are raising the whole substance, the whole pan, for example, by 1 degree Celsius. But with specific heat, we're only taking 1 gram of each substance. So 1 gram out of the small pan or 1 gram out of the large pan. And since it's just 1 gram of each, it's going to be the same value for each of them, as long as the pans are made of the same material as each other. So our specific heat equation is similar to the heat capacity equation, except we have mass involved in it. We need to know the mass of the object in order to get the mass per 1 gram Celsius, per 1 gram of the substance. So we're going to take the quantity of heat, Q, that is put into heating up the pan, and divide by the mass of the pan and the temperature change. So for the small pan, we have a small amount of heat on the top, 18,140 joules, and a small mass on the bottom, 808 grams. And the temperature change is going to be the same for both of them. For a large pan, we have a large heat on the top and a large mass on the bottom. And so when we divide those by each other, it ends up being the same amount in each case. So our specific heat for both the large pan and the small pan end up being 0.449 joules per gram Celsius. So specific heat is going to be a constant for any particular type of substance. So water will have a particular specific heat, iron will have a specific heat, steel would have a specific heat, all sorts of things have a constant specific heat. So we can actually find those specific heats in a table such as this one. So this is in your slides for you to reference back to as you're doing your homework problems. So there are a variety of different specific heats listed in there. Some of them are just single elements like helium. Some of them are compounds like water. But each pure substance has its own specific heat that's associated with it. The state of matter is going to be important for the specific heat. So liquid water would have a different specific heat from ice. So you can see liquid water has a specific heat of 4.184, whereas ice, solid water, has a specific heat of 2.093. These particular specific heats are measured at 1 bar of pressure and 25 degrees Celsius. So at different pressures and temperatures, the values might be slightly different. So anytime that we have an equation with multiple variables in it, we can rearrange to solve for any of those variables. One of the variables that we're often going to be interested in finding is heat, Q. So if we want to, we can rearrange our equation for specific heat to solve for Q. And we would do that by multiplying both sides by m times delta T. So Q would be by itself on one side of the equation, and then on the other side, we would have mass, specific heat, and change in temperature. So our equation is Q equals mc delta T. I remember this equation because it looks a lot like MCAT, the test that students take as they're preparing to enter medical school. So it's not really an A, it's a delta, but it looks pretty similar. So the delta T is going to be change in temperature, and that's going to be final minus initial, not the other way around. So it's going to be really important that you do it in that correct order. So if we wanted to, we could plug those into our equation and write it as Q equals mc times T final minus T initial. So we really have several things in this equation. We could solve for Q, we could solve for M, we could solve for C, we could solve for T final, or we could solve for T initial, as long as we know all the other variables besides the one we're trying to solve for. So here's an example where we're trying to calculate how much heat is absorbed or released. So we have a flask containing 8 times 10 to the 2 grams of water, and it's heated, so the temperature is increasing. It goes from 21 degrees Celsius to 85 degrees Celsius. So we have our initial temperature of 21 and our final temperature of 85. And it's asking how much heat the water absorbed. We're going to use the specific heat of water, specifically liquid water, which is 4.184 joules per gram Celsius. So we're going to plug what we know into our equation, Q equals mc delta T, or in other words, Q equals mc times T final minus T initial. So we plug in the 8 times 10 to the 2 grams as our mass of the water that's heated. We plug in the specific heat of water, which is 4.184 joules per gram Celsius. And we plug in our two temperatures, final minus initial. It ended up at 85, so we list that first, and it started out at 21, so we list that second. So we'll do 85 minus 21. Notice the units end up canceling out. So grams will cancel out with the grams in the denominator of our specific heat. The degrees Celsius in the denominator of our specific heat will cancel out with the degrees Celsius in our temperatures, and we'll be left with joules, which is a common unit for heat. Remember, energy takes the form of heat or work. So heat and energy are basically synonymous. Heat is a type of energy. So when we plug in all of our numbers, do the calculation, we come out with 214,221 joules. And that's how much heat the water absorbed. We could put this into scientific notation just to make the number a little bit more manageable. So we could write it as 2.1 times 10 to the 5th joules. Or we could put it into kilojoules and write it as 2.1 times 10 to the 2 kilojoules. We'll often change from joules into kilojoules just so we can get a smaller value for our number. So the sign on the Q is going to be important. It's going to be related to whether the heat is absorbed or released. Since Q is positive here, that's going to tell us that heat is going in. It's being added to the substance. In this case, heat is being added to the water. So that tells us that the water is absorbing heat. So here's a question for you to try. You're going to calculate the amount of heat needed to heat 725 grams of water from 22.1 degrees Celsius to 110.5 degrees Celsius. And you're given the specific heat of water. The correct answer is C, 268.2 kilojoules. So you're using your equation Q equals mc delta T, where m is your mass of 725 grams, C is the specific heat of water, which is 4.184 joules per gram Celsius, and delta T will be T final minus T initial, so that will be 110.5 minus 22.1. And that gives you overall 268.2 kilojoules. So when we want to measure the change in heat in the lab, we're going to do it using calorimetry. So the instrument that we use for doing that is called a calorimeter. Remember, calories are a common unit of energy or heat. So calorimetry is just measuring calories, measuring amount of heat that's transferred. So as we do calorimetry problems, it's going to be important to define two separate things, the system and the surroundings. The system is the substance that you're interested in that's undergoing the chemical or physical change. The surroundings are going to be everything else. They're going to be the other components of the measurement apparatus, the things on the outside, and they're going to give heat to the system or absorb heat from the system. But the system is going to be what we're going to be defining everything by, the thing that we're interested in. And the surroundings will be everything else. So in an exothermic process, remember exo means out, so heat is going out of the system. Everything is defined by the system. So for exothermic, heat is going out of the system and into the surroundings. So the surroundings are going to heat up. Often, our thermometer will be stuck down in some water, which would be the surroundings. So what we're measuring is the surroundings, which might be heating up or cooling down. But our definition is based on what's happening to the system. So if our system heats up, that's going to be endothermic. If our system cools down, that's going to be exothermic. So with exothermic, heat is going out of the system into the surroundings, and the surroundings end up getting warmer. In an endothermic process, heat goes from the surroundings into the system. Endo means into. So heat is going into the system and it's going away from the surroundings. So the surroundings get cooler. So you see that thermometer level dropping for an endothermic process. So in the lab, we could use a coffee cup calorimeter, which consists of a couple of styrofoam cups stacked together to create some insulation. And then there's a lid, and then we can stick the thermometer down through the lid. There may also be a stirrer placed in there, or you might just stir with the thermometer. So the assumption is that the styrofoam cup is going to contain the heat. So we would say that the heat is kind of trapped in that cup. It's not going out or in. So whatever heat is in there is going to be contained. So we will assume, using the coffee cup calorimeter, that whatever heat leaves the system is going to go into the surroundings, but not outside the cup. And whatever heat comes from the surroundings would go into the system. And there would be this change of heat from one to the other, from the system to the surroundings or from the surroundings to the system. But we would assume it would be all completely contained within that cup. So we can express this mathematically just by changing the sign on our measurement. So the Q of the system is going to equal the negative of the Q of the surroundings. It's not saying that the system is always positive and the surroundings is always negative. It's saying that they're going to have opposite signs. So if the system is negative, the surroundings will be positive, or vice versa. Similarly, the Q of the surroundings equals the negative of the Q of the system. They have the same magnitude, but opposite signs. So if one of them's a positive 81, the other will be a negative 81. With commercial calorimeters, they're going to work in very similar ways. They'll just be a little bit more sophisticated. So instead of having styrofoam as an insulator, there are metal containers. Instead of having just a little stirrer, there might be a motorized stirrer. Instead of having just a bulb thermometer stuck in, there could be a digital thermometer stuck in. So they're just a little bit better in various different ways, but they're also significantly more expensive. So we're going to do some calculations related to calorimetry. So one of the common types of experiments that students do is placing a hot piece of metal into cool water and measuring the heat involved in the transfer from the hot metal to the cool water. So in this example, the metal would be the system. It's the thing that we're interested in. And the water would be the surroundings. So remember, the system and the surroundings have the same magnitude but opposite signs. So the Q of the metal equals the negative of the Q of the water. Again, that's not saying that the metal is necessarily positive and the water is necessarily negative. It's just saying they have opposite signs. So in this case, the Q of the metal is going to be a negative number because heat is going out of the metal. Heat is lost from the metal. You can think of it as being subtracted from the metal. So the Q is going to have a negative number for the metal. For the water, it's going to be a positive number because heat is being added to the water. It's being gained by the water. So let's look at this example for calculating a specific heat of a metal using calorimetry. We're told that a 59.7 gram piece of metal was submerged in boiling water and then transferred to 60 milliliters of water that had an initial temperature of 22 degrees Celsius. The final temperature of both the water and the metal, remember they come to an equilibrium temperature, is going to be 28.5 degrees Celsius. We're also given the specific heat of water in the problem. You do not need to memorize that. What we're trying to find is the specific heat of the metal. And based on that specific heat, we can look up the value in a table and make a guess about the identity of the metal. So as we do this type of problem, it's going to be really important to identify our variables correctly. We're going to need to identify our variables for both the system and the surroundings. In this case, the metal and the water. And we're going to have Q, M, C, delta T for each of those. So for the metal, we know several pieces of information. We know the mass of the metal is 59.7 grams. The specific heat of the metal, C, is going to be unknown. That's what we're trying to solve for in this problem. The initial temperature of the metal is 100 degrees Celsius. We know its initial temperature is 100 because it said the metal was submerged in boiling water. And so we assume that it was allowed to equilibrate and have that same temperature as the boiling water. And then the T final of the metal is going to be 28.5 degrees Celsius. Again, that's that equilibrium temperature. For the water, we know the mass of the water is 60 grams. How do we know that? We're told that the volume of water is 60 milliliters. And water has a density of 1 gram per milliliter. So anytime we're talking about water specifically, not any other substance, but water specifically, if we're given the milliliters, then we can just change those milliliters to grams and they're the same thing. So the mass of the water is 60 grams. The specific heat of the water is given to us in the problem, and that's 4.184. The initial temperature of the water is 22, and that final temperature is again 28.5. So that 28.5 is the final temperature of both the water and the metal. So our first step is going to be solving for the Q of the water. That is the amount of heat that's absorbed or released by the water. So we're plugging into our equation Q equals mc delta T. And each of our variables has to be related to the water. We can't mix and match water and metal. They have to be, one time we do the equation with the water, a different time we'll do the equation with the metal. So right now we're doing the equation with the water. We plug in our mass of the water, which is 60 grams. We plug in our specific heat of the water, which is 4.184. And we plug in our temperatures for the water. Again, delta T is going to be final minus initial. So we'll do our 28.5 minus our 22. So we come out with 1,631.76 joules as the Q of the water. Notice this is a positive number, which indicates that the water is absorbing heat, which makes sense since the heat is going from the metal into the water. In our second step, we're going to find the Q of the metal. And that's going to be based on the Q of the water we just solved for. Remember, the metal and the water are going to have the same magnitude for their Q, but opposite signs. So we're just going to slap a minus sign on that 1,631.76 joules. And that's going to be our Q for the metal. In our third step, we're going to plug in that Q of the metal that we just solved for into our Q equals mc delta T equation. So this time our unknown variable is going to be the specific heat, C. And again, as we use this equation, all of our variables need to be related to the same thing. In this case, they all need to be related to the metal. So we plug in our Q of the metal, which is negative 1631.76 joules. We plug in our mass of the metal, which is 59.7 grams. We plug in the two temperatures, final minus initial. So it's going to be 28.5 minus 100. Notice that's going to give us a negative value for our delta T, a negative 71.5. But we also have a negative value for our Q. So those negative signs are going to end up canceling out and giving us a positive value for C. So our answer is 0.382 joules per gram Celsius, and it's a positive value. We can look that up in the table and find that it's likely to be copper. So here's a question for you to try. It's another calorimetry problem where we have a hot piece of metal dropped into cooler water. And what we're trying to find is the specific heat of the metal. So the answer is C, 2.4 joules per gram Celsius. So as you solve this problem, follow those same three steps. First, solve for the Q of the water. Second, just change the sign on that to solve for the Q of the metal. And then third, plug in that Q of the metal into your equation for everything related to the metal and solve for C of the metal, that is the specific heat of the metal. Let's look at another type of calorimetry problem. So here we have a problem where we have a salt dissolving in water. Remember, when I use the word salt, it could be any type of ionic compound. So this is what's happening in an ice pack. Solid ammonium nitrate is going to dissolve in water. So when you break open the little bag inside, the ammonium nitrate gets out into the water, or the water gets out to mix with the ammonium nitrate. And so the reaction occurs, and as the ammonium nitrate dissolves in the water, it's going to be an endothermic process. Heat goes into that ice pack. So in this example, we have 3.21 grams of ammonium nitrate dissolving in 50 grams of water, and that water starts out at 24.9 degrees Celsius. Then the temperature decreases to 20.3 degrees Celsius. We want to find Q for the reaction. So we're going to use our equation Q equals mc delta T. This time we're doing it related to the solution. The solution is going to be made up of the salt mixed with the water. So it's both things combined together. So rather than doing the equation twice, we're just going to do it once, but everything related to the solution. So Q of the solution equals mc delta T of the solution. So the mass of the solution is not just our 3.21 grams of ammonium nitrate, but it's also the 50 grams of water. And it's not just the 50 grams of water, it includes the 3.21 grams of ammonium nitrate. We have to have both of those masses added together to give us our total mass of the solution, which is 53.21 grams. The C for the solution, we're going to assume the solution is mostly made of water, so its specific heat should basically be the same as water, which is 4.184 joules per gram Celsius. And we have two temperatures, an initial temperature of 24.9 and a final temperature of 20.3. Now remember, for delta T, we're going to do final minus initial. So we plug in our equation, our mass of 53.21, our specific heat of 4.184, and our two temperatures, final minus initial, 20.3 minus 24.9. So we get a negative value for our delta T, which ends up giving us a negative value for our Q. And that value is going to be negative 1024.1 joules. The reaction is actually going to have the opposite sign of the Q for the solution. So we would say the reaction would be a positive 1024 joules. So 1024 joules go into the reaction. They go out of the surroundings. So that's why the surroundings cool down, but the reaction itself is heating up. Here's another type of process that we can look at with calorimetry. This is a neutralization reaction between an acid and a base. So we have 50 milliliters of 1 molar HCl reacting with 50 milliliters of 1 molar sodium hydroxide. And they both start out at a temperature of 22 degrees Celsius. When they get mixed together, the temperature heats up to 28.9 degrees Celsius. We want to find the amount of heat produced by this reaction. So again, we're going to use the equation Q equals mc delta T with everything related to the solution. The mass of the solution, that is the mixture of the hydrochloric acid and the sodium hydroxide, is going to be the total of 50 plus 50. Again, our solutions are mostly made up of water, which has a density of 1 gram per milliliter. So if we have 50 milliliters of hydrochloric acid solution and 50 milliliters of sodium hydroxide solution, then we're going to assume that they're both 50 grams. So when we add them up, we get a total of 100 grams of solution. C, the specific heat of the solution, we're going to assume, since our solutions are mostly water, we'll use the C of water, which is 4.184. And then our two temperatures, the final temperature is 28.9, and the initial temperature is 22. And again, we're doing final minus initial. So our Q for our solution is 100 times 4.184, and then we multiply by 28.9 minus 22. And that gives us 2887 joules. Again, The reaction is going to have the opposite sign of the Q of the solution. So the reaction has the negative 2,887 joules. So heat is going out of the reaction. It's going into the solution. So we could say that 2,887 joules are produced by the reaction. Another type of calorimeter is a bomb calorimeter. With these types of calorimeters, the heat capacity of the calorimeter will be used in our calculations. So we're going to use some equations that we've already seen in just slightly different ways. So we'll use a rearrangement of the heat capacity equation. Remember, heat capacity is going to be Q over delta T. So we can rearrange that to solve for Q. We get Q equals heat capacity, that's capital C, times delta T. And we're going to use that all in relationship to the calorimeter. We're also going to assume that the surroundings are made up of both water and the calorimeter itself. So the sum of the heat in the water and the calorimeter itself will have the opposite sign of the Q of the sample. So Q of the sample is our system, and then the Q of the surroundings is our water and the calorimeter combined. So in this example, we have 3.12 grams of glucose being burned in a bomb calorimeter. The temperature of the calorimeter increases from 23.8 degrees Celsius to 35.6 degrees Celsius. The calorimeter contains 775 grams of water, and the bomb itself, that is the calorimeter, has a heat capacity of 893 joules per degree Celsius. What we're trying to solve for is how much heat is produced by the combustion of the glucose sample. So first of all, we're going to do a calculation based on the calorimeter itself, using the heat capacity of the calorimeter. So we can plug in the heat capacity, which is our capital C, and that's 893 joules per Celsius. And we plug in our change in temperature for our calorimeter. Again, final minus initial. So it ended up at 35.6, and then we subtract the 23.8 that it started out as. So we come out with 10,537 joules is the Q for the calorimeter. The Q for the water, we're going to calculate based on the Q equals MC delta T. So we have a mass of the water, which is 775 grams. The specific heat of water is that same 4.184 that we've been using all along. And the temperature of the water is going to end up being the same temperatures as for the calorimeter. So we're still going to do that 35.6 minus the 23.8 for our water as well as for our calorimeter. So for the water, we end up with a heat of 38,263 joules. So we can add up those two numbers, and the opposite sign of that will give us the Q of our sample. So we can have negative of 38,263 plus 10,537. And that gives us negative 48,800 joules as the Q of our sample. We can put that in kilojoules to give us a nice, more manageable number of negative 48.8 kilojoules. And that negative sign is telling us that heat is being released. It's going out of the sample. So when you look on your box of macaroni and cheese or your cereal boxes, you see those big C calories listed. The way those are found is by using a bomb calorimeter. So the sample has to be prepared. It's going to be weighed, mixed in a blender, freeze-dried, ground into powder, and formed into a pellet. And then once it's prepared, it's put into the bomb calorimeter and burned. And based on the values, you can calculate the heat that is released from that process of burning it. And so we can find the calories by doing that. In this next section, we're talking about a concept called enthalpy. Before we can get to enthalpy, we're going to talk about a few other definitions. So internal energy, we're going to abbreviate with a capital U. And it's going to be the total of all of the possible kinds of energy present in a substance. So it might have some thermal energy based on the motions of the molecules. There's a variety of other types of energy present as well. So the first law of thermodynamics tells us that energy can't be created or destroyed. It's only converted from one form to another. And we can express this in equation form related to the system and surroundings. So we could say delta U for the system, that is change in internal energy for the system, plus delta U for the surroundings, change in internal energy for the surroundings, equals 0. That is, there's no net change. There can be a movement of energy from the system to the surroundings or from the surroundings to the system, but there's no net change. No energy is lost during the process. We could rearrange that equation to say the delta U of the system equals the negative of the delta U of the surroundings. This is basically the same thing as our Q of the system equals our negative Q of the surroundings. But with this, we're talking about all of the types of energy, not just heat, but there are other types such as work. So we're going to use the equation delta U of the system equals Q plus W, where Q is heat and W is work. So if we add up the heat and the work, that gives us all of our energy for the system. So as we use this equation, it's deceptively simple. It seems like we're just going to be adding two numbers. The tricky part is that we have to identify the signs for each of those numbers. We're going to be working with word problems, and the sign may not be explicitly stated in the word problem. So you have to think about what is happening with relationship to the system and the surroundings. We've already talked about the appropriate signs for Q. When heat is going into the system, that is absorbed by the system, that is for an endothermic process, the Q is going to be a positive value. When heat is released by the system, it's going out of the system, being subtracted from the system, that is for an exothermic process, the Q is negative. We can have similar sign conventions for work. When work is done on the system by the surroundings, we give that a positive sign for W. So you can think of work as being added to the system. In this case, work is done on the system. So we give it that positive symbol. If work is done on the surroundings by the system is doing the work. So the system is going to be sort of releasing work. Work is going out of the system, so we give it a negative sign. So we can look at our word problems, and based on what is happening to the system or the surroundings, we'll give it a positive or a negative sign for the Q and or the W. So again, everything is based on what's happening to or with the system. So if there's an increase in work or heat for the system, the delta U for the system will increase. If there's a decrease in work or heat for the system, the delta U will decrease. So here's an example of one of the word problems you might encounter. Again, you're going to use that equation we just talked about. Be careful with the signs, and be careful that the units are the same as each other. Anytime you're trying to add something or subtract something, really for any of your calculations, the units need to be consistent. So the correct answer is going to be C. negative 102 joules. So the first thing you're going to have to do is get the units to be the same as each other. So I would change the kilojoules of work into joules. When we do that by multiplying by 1,000, we end up with 31 joules. But we don't know the signs yet. We have to actually read the words in the word problem. So it says that the system releases 71 joules of heat. So 71 joules of heat are going out of the system. So the 71 is actually going to be a negative. And it also says that the work is being done on the surroundings, that is, by the system on the surroundings. So that's also going to be a negative value. So we'll have negative 71 for the heat and negative 31 for the work, making a total of negative 102 joules. So we're going to be looking at enthalpy, which is a state function. A state function is a function that does not depend on how the state is reached. It only depends on what state the system is in. So an example is climbing a mountain. You could climb it basically from straight at the bottom, straight to the top. Or you could take a more circuitous route that's a bit less steep, but you have to walk for a longer distance to get there. In the end, it doesn't really matter because you're going to reach the same elevation in the end. So the state function would be the altitude or elevation that you're trying to get to at the top. Or in other words, the difference between the summit and the base. So enthalpy is an example of a state function, and we use the letter capital H to represent enthalpy. Our official definition of enthalpy is going to be U, the system's internal energy, plus PV, where P is pressure and V is volume. We can calculate a change in enthalpy, and to do this, we would have some deltas in our equation representing change. So we have delta H, change in enthalpy, equals delta U, change in internal energy, plus pressure times the change in volume, P times delta V. So that's going to be our official definition for change in enthalpy. But really, as we go about our calculations in this chapter, what we're really going to be the most useful is the fact that delta H, change in enthalpy, is going to be equivalent to Q at a constant pressure, so Q sub P. So heat and enthalpy are basically interchangeable as long as the process is happening at constant pressure. So I'm going to refer to things related to enthalpy as heat. I'm going to refer to things related to heat as enthalpy. They're basically interchangeable. We're going to have some rules for using delta H. So first of all, the value for delta H will be supplied alongside a chemical equation. And that delta H refers to the amount related to a particular number of moles of the reactants and products the way it's written in the chemical equation. So if you have coefficients of 2, 2, and 2, and a particular delta H associated with that, if you were to change those coefficients to, let's say, 4, 4, and 4, you would have a new value for your delta H. So let's say we multiply our coefficients by some value. We're actually going to multiply the delta H by that same value. So if we multiply our coefficients by 2, we'll multiply our delta H by 2. If we divide our coefficients by 2, we'll divide our delta H by 2. And this is because delta H is an extensive property. Remember, extensive properties depend on the amount of matter present. So if there are 4 moles of each thing, that's going to have a different amount of energy associated with it compared to 2 moles of each thing. Also, the enthalpy change, the delta H, is going to depend on the physical state of the reactants and products. So whether it's a solid, a liquid, a gas, aqueous solution, that's going to affect the values that we're plugging into our calculations. So we need to know the states of the matter. It's going to be really important for this chapter. If we get a negative value of delta H, that's going to tell us that our reaction is exothermic. If we get a positive value of delta H, that's going to tell us our reaction is endothermic. Remember, delta H and Q are basically interchangeable. So if we have a negative value of Q, that's exothermic, a positive value of Q is endothermic. So the same thing is going to be true for our delta H's. And then our last rule is that if we reverse an equation, that is, if we put the products on the reactant side and the reactants on the product side, then the sign on the delta H needs to be reversed. So if it was positive, we change it to a negative. If it was negative, we change it to a positive. So here's an example of a calculation we can do to find enthalpy change. So we have an equation given to us in the problem of hydrochloric acid reacting with sodium hydroxide to make sodium chloride and water. And we're told that when 0.05 moles of HCl reacts with 0.05 moles of sodium hydroxide to form 0.05 moles of sodium chloride, then 2.9 kilojoules of heat are produced. What we want to find is the enthalpy per mole of acid that reacts. Essentially, since our balanced chemical equation has coefficients of 1 in front of each thing, the equation, the way it's written, is 1 mole of HCl reacts with 1 mole of sodium hydroxide to make 1 mole of sodium chloride and 1 mole of water. But if those coefficients are changed, then the delta H changes along with it. So when we actually did this in the lab, we had 0.05 moles of each thing in the reaction, and 2.9 kilojoules were associated with that particular amount. So since we're trying to find the amount per 1 mole of hydrochloric acid, we're going to start with that as our initial value. And then we'll use the relationship between moles of acid and kilojoules of heat that we know from the reaction that was done. So for the reaction that was actually done, there was only 0.05 moles of acid put in, and only 2.9 kilojoules of heat were produced. But we're trying to find out what happens when 1 mole of acid is put in. So we want moles of HCl on the bottom to cancel out, and kilojoules is going to go on the top since we're trying to find the amount of enthalpy, the delta H, per mole of acid. So we have 1 times 2.9 divided by 0.05, and that gives us 58 kilojoules would be associated with our 1 mole of acid. So this problem is very similar to the previous one in that you can use a known relationship between a delta H and a coefficient from the chemical equation in order to solve for something that's unknown. In this case, we have a balanced chemical equation given to us and a delta H associated with that balanced chemical equation. So when we have 2 moles of iron, negative 824.2 kilojoules of heat would be produced. And the question is, what mass of iron would be needed to make negative 335 kilojoules of heat? Notice it's asking for mass of iron, so all your answers are in grams. But our relationship is between kilojoules and moles. The correct answer is A, 45.4 grams. So you're going to take your negative 335 joules as your starting value and use a conversion factor between heat and moles. Our conversion factor is that for every 2 moles of iron, negative 824.2 kilojoules of heat are produced. And that would give us our number of moles of iron that would be needed. Then we can take those moles and convert them into grams using the molar mass of iron. We can do this type of calculation with limiting reactants. Anytime that you're given two different starting masses, the masses of two different reactants, it's going to be a limiting reactant problem, whether it says so or not. So we have 2.67 grams of sucrose reacting with 7.19 grams of potassium chlorate. That doesn't necessarily mean that all of the sucrose or all of the potassium chlorate will get used up. So we're first going to have to find which is the limiting reactant. We're told when that reaction happens, 43.7 kilojoules of heat are produced. And we want to find the enthalpy change for the reaction. And what's implied by that is we want to find it for the reaction in our equation as written. So when we have 1 mole of the sucrose reacting with 8 moles of potassium chlorate to make 12 moles of CO2, 11 moles of water, and 8 moles of potassium chloride, how much heat or enthalpy would be associated with that? So the first thing we're going to have to do is go from grams of sucrose to moles of sucrose by dividing by the molar mass of sucrose. Notice that grams cancels out with grams, and that molar mass always goes next to grams. So that gives us 0.00780 moles of sucrose. Then we can go moles of sucrose to moles of CO2 using our stoichiometric factor from our balanced chemical equation. There's a 12 next to the CO2, and there's an understood 1 next to the sucrose. So we're multiplying by 12, and that gives us 0.0936 moles of CO2. Now we're going to do the same type of calculation, but with our other reactant, the potassium chlorate. So we're going to go from grams of potassium chlorate to moles, and then moles of potassium chlorate to moles of our product, the CO2. If we wanted to, we could have chosen moles of water or moles of KCl for our comparison. We just have to choose one of our products and be consistent about it. So we take our 7.19 grams of potassium chlorate, divide by the molar mass of potassium chlorate, which is 122.5. Again, grams cancels out with grams, and that molar mass is on the bottom next to grams. So we come out with 0.05869 moles of potassium chlorate. Then we go from our reactant to our product, again using a stoichiometric factor. So we have a 12 in our equation next to the CO2 and an 8 next to the potassium chlorate. And notice the moles of potassium chlorate are canceling out with each other, and we're left with moles of CO2. So we come out with 0.0880 moles of CO2. When we compare that value to the value based on our other starting material, the sucrose, this value is the smaller of the two values. The 0.0880 is the smaller of the two values, which means the potassium chlorate is the limiting reactant. So we're going to do our relationship based on the potassium chlorate. But we want to do it with our equation as written. So if we have 8 moles of potassium chlorate, then we can use our relationship between moles of potassium chlorate and kilojoules of heat that gets produced. Our moles of potassium chlorate is that 0.05869 that we just calculated at the top of this slide. And the 43.7 kilojoules of heat is what was produced out of that reaction. So we have the relationship between the moles of potassium chlorate, our limiting reactant, and the amount of heat produced by this reaction. And we can use that as a conversion factor to go from moles to the enthalpy. So we're going to do 8 times 43.7 divided by 0.05869, and that gives us 5957 kilojoules for the equation as written. So we're going to look at some specific types of reactions that we can find the enthalpy for. One particular one is the enthalpy of combustion. So this would be the enthalpy for a particular combustion reaction. We can write the standard enthalpy of combustion, and standard we're going to represent with a little degree symbol. So the standard enthalpy of combustion will be the enthalpy change when 1 mole of a substance burns under standard state conditions. So the standard state conditions that we're talking about here are going to be 1 atmosphere of pressure and 25 degrees Celsius. So that little degree symbol is representing those particular conditions of temperature and pressure. So we could burn carbon, for example, react it with oxygen, and turn it into CO2. And the change in enthalpy for that reaction has been measured to be negative 393.5 kilojoules per mole. And you can see a variety of different other substances in this table as well for you to refer to. So here's an example of an enthalpy of combustion. So we have the combustion of gasoline, and we're trying to figure out how much heat is produced by burning 1 liter of gasoline. So we're going to assume the gasoline is basically made up of isooctane. So if we look up isooctane in our table, we can find its equation and its delta H associated with it. We're also given in the problem that the density of isooctane is 0.692 grams per milliliter. So we're going to take our 1 liter of isooctane, in other words, gasoline, and change it into milliliters. We're changing it into milliliters so that we can use the density as a conversion factor to go from milliliters into grams. So we're dividing by 10 to the minus 3, and that gives us 1,000 milliliters of isooctane. Then we can go from milliliters into grams using the density. We're told the density is 0.691 grams per 1 milliliter. So again, that per essentially means divided by. So 1,000 times 0.691 gives us 691 grams of isooctane. Then we can go from grams into moles by dividing by the molar mass of isooctane. So we do 691 divided by 114.232, and that gives us 6.049 moles of isooctane. Now we can finally use our balanced equation that tells us that for each 1 mole of isooctane, negative 5,461 kilojoules of heat would be associated with that. So since we don't have 1 mole, we have 6.049 moles. We need to do a little bit of a calculation. So we do 6.049 times negative 5461, and that gives us negative 33,034 kilojoules. By the way, this is the amount of energy needed to melt 99.2 kilograms, or in other words, 218 pounds of ice. And that's just in our 1 liter of gasoline. Another special type of reaction that we're going to be interested in the delta H for is going to be standard enthalpy of formation. Again, the standard symbol is represented with a degree, and we have F as our subscript indicating formation. So the standard enthalpy of formation is going to be the enthalpy change for a reaction when we have 1 mole of a pure substance being formed from free elements in their most stable states under standard state conditions. So several things have to be true for this to be a standard enthalpy of formation type of reaction. We're going to have a single product, so just one thing on our right-hand side, and it has to have a coefficient of 1 because we're talking about exactly 1 mole of that substance being formed. The reactants have to be single types of elements, the way we find them in nature. So for example, oxygen will be found as O2 gas. The coefficients with those reactants may end up being fractional. So in this chapter, we're going to be manipulating our equations. And as we do, we may end up with some fractional coefficients, and that's going to be okay. So rather than having it be the lowest whole number ratios, we're going to change things around in order to do the calculations that we need to do. So here are some examples of equations for standard enthalpy of formation. So let's say we wanted to find the enthalpy of formation of CO2. So in that equation, we have CO2 as our single product on the right-hand side, and it has a coefficient of 1. On the left-hand side, we have the elements that are needed to make up CO2. We've got carbon and we have oxygen, and they're in their standard forms. So carbon in the earth is found as solid, usually as graphite, and O2 gas is how we find the oxygen. So our equation for the enthalpy formation is carbon solid plus O2 gas makes CO2 gas. And the enthalpy of formation, that is the enthalpy associated with that reaction as written, is negative 393.5 kilojoules. We can do another example with NO2. So the NO2 is the single product on the right-hand side, and it has a coefficient of 1 because we're finding the amount of energy needed to make 1 mole of that substance. On our left side, we have nitrogen and oxygen, the way we find them in nature. So nitrogen is found as N2 gas, oxygen is found as O2 gas. And we have the coefficients needed to make the correct number of atoms on the right-hand side. On our right-hand side, we have 2 oxygens, so our O2 molecule on the left is fine. We've got 1 nitrogen, so our N2 molecule as is would not be okay. We would actually need to put a coefficient of 1/2 in front of that to indicate that we have 1 nitrogen atom. 1/2 of an N2 molecule would be 1 nitrogen atom, and that matches up with our 1 nitrogen atom on our right-hand side. So these do still need to be balanced. They just might end up with some fractional coefficients on our left side because we're stuck with our right side having a coefficient of 1. And so the enthalpy of formation of NO2 ends up being a positive 33.2 kilojoules. So let's write out some enthalpy of formation equations. Here we're writing the equation for C2H5OH, that is ethanol. So we need to have the thing we're trying to form on our right-hand side, and that's going to be our only product, and it's going to have a coefficient of 1. On our left side, we need to have the elements that are needed to make it up. So we're going to have carbon, hydrogen, and oxygen. And they're going to be in their elemental forms, the way we find them in nature. So carbon is going to be solid, graphite, hydrogen is going to be found as H2 gas, and oxygen is going to be found as O2 gas. As you do these types of problems, you're going to get a sense for what are the elemental forms that each of these elements come in. We also need to make sure that our equation is balanced. So on our right side, we have 2 carbons, 6 hydrogens, and 1 oxygen. So on our left side, we're also going to need to have a total of 2 carbons, 6 hydrogens, and 1 oxygen. But we're stuck with the particular ways of writing each element. So if we want 2 carbons, we can just put a 2 in front of our carbon solid graphite. If we want 6 hydrogens, we can put a 3 in front of our H2 gas. So 3 times 2 gives us 6. And then if we want 1 oxygen, we're going to have to put a 1/2 in front of our O2 gas. So 1/2 times 2 gives us 1, which matches up with the 1 we have on the right-hand side. So our equation for the enthalpy of formation of ethanol is going to be 2 carbon solid graphite plus 3 H2 gas plus 1/2 O2 gas makes our ethanol. Sometimes we'll be given an equation and we'll want to manipulate it to get it into the correct form. Our enthalpy of formation reactions have a very specific form that they need to be in order for it to count as an enthalpy of formation. So in this example, we have a reaction of 3O2 going to 2O3 gas. And the delta H for that reaction is 286 kilojoules. What we want to find is the delta HF of ozone, the enthalpy of formation of ozone. So we need ozone to have a coefficient of 1 in front of it for it to be a true enthalpy of formation reaction equation. What we're going to do is divide our equation by 2. So each of the coefficients in the equation get divided by 2. So 3 divided by 2 gives us 3/2, and 2 divided by 2 gives us 1. So we end up with a coefficient of 3/2 in front of the O2 molecule and a coefficient of 1 in front of the ozone. So we've gotten our equation into the proper form, where we have a single product on the right-hand side with a coefficient of 1, and then on the left-hand side we have an element, in this case oxygen, in its elemental form, the way we find it in nature. And so the delta H for that reaction was measured to be 143 kilojoules, and that would be the enthalpy of formation of ozone. So there are 4 ways to find the delta H. We've already talked about calorimetry, which is an experimental way to find the delta H for any reaction. There are 3 calculational ways that we can find the delta H for a reaction just by looking up values in a table. So by relying on experiments that have been done in the past, we can use some calculational ways to calculate delta H values for experiments that we are not personally doing. So those 3 ways are using delta HF values, using Hess's law, and using bond energies. So we're going to talk about each of those 3 calculational ways. So our first way to calculate delta H, if we can look up some values in a table, is based on the delta HFs of each of the products and reactants. So what we would need is a table of the delta HF values that have been tabulated for many different substances. And if we can look up all of those reactants and products in a table, we can use this equation. So our equation we have in sort of a general form and then a slightly more specific form. So our general form is our delta H standard for the reaction is going to be the sum, that sigma is standing for sum, that is adding things up, of the N, that is coefficients, times the delta HF values of the products, minus the sum of the coefficients times the delta HF values of the reactants. So let's say we have the generalized equation. Little a big A plus little b big B goes to little c big C plus little d big D. The little letters represent the coefficients, and the big letters are the chemical formulas of each of the reactants and products. So our delta H for a reaction is going to be stuff from our product side, the stuff on the right-hand side, minus stuff on our reactant side, the stuff on our left. So we're starting out with C and D, and then we're subtracting A and B. So we have little c, the coefficient C, times the delta HF of product C, plus coefficient D times the delta HF of product D. And then we subtract coefficient A times the delta HF of reactant A plus coefficient B times the delta HF of reactant B. So we're going to multiply the delta HF for each of the products by the corresponding coefficients and add those up. We'll multiply the delta HFs for each of the reactants by their coefficients and add those up. And we're going to do products minus reactants. One thing to keep in mind is that the delta HF for elements in their standard form is going to be 0. So it may not be explicitly listed in a table, but if it's an element in standard form, let's say oxygen gas or nitrogen gas or zinc solid, then its delta HF would be 0. Essentially, it takes 0 enthalpy to form it because it's the way it's already found in nature. So here's an example of calculating the overall delta H of a reaction based on the delta HF values of each of the parts of the reaction. So we're trying to find the delta H for the reaction between nitrous oxide and water to make nitric acid and nitric oxide. So our delta H is going to be basically our products minus our reactants. So we have to start with our first product, the nitric acid. The nitric acid has a coefficient of 2 in the balanced chemical equation, and its value from the table for its delta HF is negative 207.4. So we would multiply those together. Then we do the same type of thing with the NO. So the NO has a coefficient of 1 in the balanced chemical equation and 90.2 as its delta HF value. So we would multiply those together. And then we would add those things up. That's where that sum symbol comes into our equation. We're adding the sum of the coefficients times the delta HFs of each of the parts of the reaction. So then we're going to do the same types of things for our reactants, the things on our right side of the things on our left side of our arrow. So the NO2 is our first thing on our left side. It has a coefficient of 3 in the balanced chemical equation and 33.2 as its delta HF value. So we would multiply those together. And then the last thing is the water. It has a coefficient of 1 in the equation and a delta HF value of negative 285.8. So again, we're doing products minus the reactants. Things on the right side minus the things on the left side. And when we do this, we can do it all in our calculator all at once, as long as we are very, very careful about parentheses. So we come out with a negative 138.4 kilojoules per mole. So here is one for you to try, calculating the overall delta H for a reaction, and you're given some of the delta HF values. So the correct answer is C, negative 3,267.5 kilojoules. Remember to do products minus reactants, not the other way around. And the oxygen is going to have a delta HF value of 0 because it's an element the way we find it in nature. But all the other values were listed in the table. And remember to multiply those by the coefficients of each thing in the balanced chemical equation. Our second way of calculating the overall delta H for a reaction is using Hess's law. So Hess's law takes advantage of the state function nature of enthalpy. So if we can express a reaction as a sum of several other equations, then we can find the overall delta H, the overall enthalpy change, by adding the delta H's of each of those equations that make up the full one. So if we know the steps, we can add up the steps to get the final value. So this is another way that we can calculate enthalpy when we can't measure in the lab or we just don't want to. As long as we have equations that have been measured in the lab that are appropriate to our calculation. So here is a simple Hess's law type problem. With the formation of CO2, we've seen that the equation can be written as 1 carbon plus the O2 molecule makes the CO2. And the delta H for that reaction is overall a negative 394 kilojoules. Well, we could think of this as a two-step process where each step is adding on an oxygen. So our first step is carbon with 1 oxygen, but we're not going to express it that way in our equation because we're still going to have it expressed as a delta HF type equation where we have 1 as our coefficient on the right-hand side, and on our left-hand side we have elements the way we find them in nature. So this particular equation is written as carbon plus 1/2 of the O2 molecule, but that's equivalent to 1 oxygen atom. And so we get the CO molecule as a result. And then we can add on 1 more oxygen to that. Again, we would be adding it in the form of 1/2 of the O2 molecule to get the CO2 gas as our product. Now the delta H's of those two steps are a negative 111 kilojoules and a negative 283 kilojoules respectively. So if we add those up, negative 111 plus negative 283 gives us a total of negative 394. So we have our two steps and the delta H's along with those two steps, and we can add those two steps together to get our overall reaction. Essentially, we have carbon plus 1 oxygen, and then we're adding another oxygen, which is going to be the same thing basically as having carbon and 2 oxygens to make CO2. So we have our steps, and we can add the delta H's for those steps to get the overall delta H for the reaction. So notice when we add the two steps, it's going to be the same sort of way as when we add our redox equations together. So anything on the left side of an arrow goes down on the left side of the arrow. Anything on the right side of an arrow goes down on the right side of the arrow for our overall. And if something appears on both sides, we can cancel it out. So in this case, with our two steps, the CO appears on the right side in our first equation and on the left side in our second equation. So that ends up canceling out. So then we can just bring everything else down on the correct side of the arrow. We have carbon solid. We have 2 of our 1/2 O2s, so 1/2 plus 1/2 makes 1. So in our final equation, we have 1 O2 molecule. And then on the right side, we have our CO2 gas. So we added our two equations together for our two steps, and we add our delta H's together. And that gives us that same delta H that we experimentally measured. We can look at this pictorially. So there are really two ways to get to our destination. We could go there directly with carbon and the O2 molecule going to CO2, or we could do it in steps, where we have carbon plus 1 oxygen, and then we add another oxygen to that. So remember our rules for delta H, and we're going to really be applying them a lot in this section. So remember, if the coefficients are multiplied by some value, then the delta H has to be multiplied by that same value. So let's look at an equation. 1/2 of the nitrogen molecule plus the O2 molecule makes NO2 gas. Let's say we wanted to manipulate that equation by multiplying each of our coefficients by 2. Well, 1/2 times 2 gives us 1. 1 times 2 gives us 2 in front of the oxygen, and 1 times 2 gives us 2 in front of the NO2. So we've multiplied our equation by 2. So each of our coefficients got multiplied by 2. And then we do the same thing to our delta H. So our delta H was 33.2. We multiply that by 2, and that gives us 66.4. Our other rule is that if we reverse the equation, the sign on the delta H also has to be reversed. That is, changed from a positive to a negative or negative to a positive. So let's say we have the equation for the formation of hydrochloric acid. If we reverse that so that the HCl is on the left and the hydrogen and chlorine are on the right, we're going to change the sign on our delta H. So if it was negative, we change it to a positive. So we come out with a positive 184.6. So we're going to be doing some more complicated Hess's law problems that have multiple steps. So we'll have some overall equation that we're trying to build and some steps that we're going to use to build it. We're going to manipulate those steps if they're not in the correct form. So we're going to be checking for two things to be true for each of our steps. First of all, is the desired compound on the correct side of the equation? If not, we're going to reverse the equation and change the sign on our delta H. The second thing we're checking is, does the desired compound have the correct coefficient? If it doesn't, then we're going to multiply or divide our equation by some number and do that same multiplication or division to our delta H. So let's look at an example. We have a reaction that we're trying to build. ClF plus F2 makes ClF3. And we have three steps that we're using to build it. But if we were to add the equations together as is right now, they would not add up to the reaction that we're trying to build. So we're going to have to manipulate them. And as we do, we're checking for the particular compounds that are in our final equation. So we're looking for the ClF, and we're checking to see if it's on the correct side and with the correct coefficient. We're checking for the F2 to be on the correct side with the correct coefficient. And we're checking for the ClF3 to be on the correct side with the correct coefficient. Now, if you're given a series of steps, you will use all of them in building your final equation. We're not trying to trick you. So if we are saying that these are the steps that you need, they're going to be the steps that you need. So we have our overall equation that we're trying to build. If we want to start with our first substance in our reaction, that's going to be the ClF. And we find that in reaction 2, the second stepwise equation that we were given. So the ClF in that equation in reaction number 2 is on the correct side of the equation. It's on the left where we want it, but it has the wrong coefficient. In our stepwise equation, it has a coefficient of 2, but in our overall reaction equation that we're trying to build, it has a coefficient of 1. So they don't match, which means we're going to have to multiply or divide our equation by some number and do the same thing to our delta H. In this case, since our step equation has a 2 and we're trying to get it to be a 1, we're going to have to divide. So we're going to do divide our whole equation by 2. Not just the ClF, but everything in the equation. So all of the coefficients will be divided by 2. So we have 2 divided by 2 gives us 1 for the ClF. 1 divided by 2 gives us 1/2 for the O2 molecule. 1 divided by 2 gives us 1/2 for the Cl2O. And 1 divided by 2 gives us 1/2 for the OF2. And we do the same division for our delta H. So we had a positive 205.6. We divide that by 2, and it gives us a positive 102.8 kilojoules. So we've gotten part of our reaction the way that we want it to end up in our overall. It's on the correct side, and it has the correct coefficient. So this is very likely to be the form of reaction 2 that we want to keep. And we're going to use this particular delta H value, the positive 102.8 is going to be the value that we'll need to add up in the end. The next part of our equation that we want to make sure is correct is the F2. We find F2 in reaction number 1, but it is on the wrong side of the equation and has the wrong coefficient. We want it to be on the left, but it's on the right. And we want it to have a coefficient of 1, but it has a coefficient of 2. So we need to fix both of those things. So let's fix the side of the equation first. We're going to reverse our equation by putting our reactants on our product side and our products on our reactant side. And when we do that, we change the sign on our delta H from a negative to a positive. So we've gotten the F2 on the left side where we want it, but it still has the wrong coefficient. It has a 2, but we want it to be a 1. So we're going to divide our whole equation by 2. So 1 divided by 2 gives us 1/2 in front of the O2. 2 divided by 2 gives us 1 in front of the F2. And 2 divided by 2 gives us 1 in front of the OF2. And when we divide our equation by 2, we also have to divide our delta H by 2. So positive 49.4 divided by 2 gives us positive 24.7. So we've manipulated our equation by reversing it and dividing by 2. And we've manipulated our delta H by changing the sign and dividing by 2. Our third piece of the reaction that we're trying to get correct is the ClF3. We can find the ClF3 in reaction 3, or step 3 that we're given in the problem. But it's on the wrong side of the equation. We want it to be on the right, on our product side, but in our step equation, it's on the left. So we're going to have to reverse our equation. The good news is it has the correct coefficient, so all we have to do is reverse the equation and change the sign on our delta H. So when we reverse it, the products go on the reactant side, reactants go on the product side. And we change the sign from a positive to a negative. So this is the form of reaction 3 that we're going to want to keep, and the delta H along with it is the negative 266.7. So now that we've gotten our equations the way that we think are probably going to be correct, we're going to add our equations up to double check and make sure that our equations add up to the overall that we're trying to make. Some of the parts of the equations are just there because they were part of the reaction that was measured, and they're going to end up canceling out. But the 3 pieces that we want to end up with will end up with in our final overall equation. So first of all, the O2 gas. We have our first equation has 1/2 O2, our second equation has 1/2 O2, and those are both on the left side. And so those add up to 1, and that will cancel out with the 1 oxygen molecule on the right-hand side. OF2 is also going to cancel out. We have a 3/2 OF2 on the left of our third equation, and we have 1 and 1/2 O2, that's the same thing as 3/2, total on the right. 1 from our first reaction and 1/2 from our second reaction. And the Cl2O ends up canceling out. We have 1/2 on each side of an arrow. So the things that didn't cancel out were the ClF, the F2, and ClF3, and they have the coefficients that we wanted. So we built our overall equation that we were trying to build. Since we have double checked that we have built our equation that we're trying to build with our manipulated equations, now we can take our manipulated delta H's and add them up. So we have positive 24.7, and then we add positive 102.8, and then we add negative 266.7, and that gives us an overall delta H for this reaction of negative 139.2 kilojoules. So here's a Hess's law problem for you to try. You're given an overall equation that you're trying to build and 3 step equations that you're going to use to build it. Some of the things in these equations will just be there to cancel out. So keep that in mind and make sure you're looking for things to be on the correct sides of the equations and have the correct coefficients. The correct answer is D, negative 304.1 kilojoules. So the first equation is actually fine as is. It has NO and NO2 in it. And both of those have a coefficient of 1, which is what we want in our final equation that we're trying to build. and they're both on the correct side of the equation. So we're going to leave reaction number 1 alone. Reaction number 2 is actually just going to be there for canceling stuff out. So we would want to maybe save reaction number 2 for last. Reaction number 3 has the oxygen in it, but it's on the incorrect side, and it has the incorrect coefficient. So we're going to have to reverse the equation and divide by 2. So for our delta H, we would change the sign and divide by 2. And then our second equation, again, since it's just there to cancel things out, is still going to have to cancel them out in the correct way. So since we have ozone on our left side in reaction number 1, we need ozone on our right side of reaction number 2 to cancel out. So we're going to have to reverse that equation, and we would change the sign on our delta H. Once we've done all of those manipulations, we can add them up and add up our delta H's to get the correct answer. In this section, we're going to be talking about strengths of ionic and covalent bonds. We're going to be using covalent bond strengths in order to calculate overall delta H of a reaction. So in order to break a chemical bond, energy has to be added. It's an endothermic process. We have to put energy in order to break a bond. Breaking bonds takes energy. To form a chemical bond, on the other hand, is going to release energy. That's going to be an exothermic process. So for example, we could go from the H2 molecule to 2 individual hydrogen atoms, and that process would be a positive 436 kilojoules for its delta H. We have to add energy to make it happen, to break that bond. For the other reverse process, where we have 2 hydrogen atoms combining together to make the hydrogen molecule, a bond is being formed, and that's going to release energy. So the overall delta H of that process is a negative 436 kilojoules. We can calculate the bond strength of a covalent bond by measuring the delta H for the reaction where we take a diatomic molecule and break it apart. So if we have the molecule XY and break it apart into an X atom and a Y atom, we can measure the delta H for that reaction, and that would be the bond energy for that diatomic molecule. So for example, if we break apart the H2 molecule and measure that reaction, that would be the bond energy of the H2 bond, the bond between the 2 hydrogens, which is the single bond. We can also look at larger molecules like methane, which is CH4. If we were to break apart methane into individual atoms, we would have 4 bonds being broken. And the overall delta H for that reaction, where we take methane and break it apart into carbon and 4 hydrogens, is 1,660 kilojoules. But that's going to be covering 4 bonds being broken. So if we want to find the average CH bond energy in methane, we're going to take that 1,660 and divide it by 4, and that tells us that each individual bond has an energy of 415 kilojoules per mole. So to calculate the overall delta H for a reaction from bond energies, we're going to take the sum of the bond energies for all of the bonds that get broken and subtract the sum of the bond energies for all of the bonds that get formed. Another way of thinking about this is we're going to take the sum of the bond energies of the reactants and subtract the sum of the bond energies of the products. So the reactants are having their bonds broken, and the products are having their bonds formed. So we're doing reactants minus products in this case. You're going to need to draw out the Lewis structures of all of the reactants and products to make sure you know exactly what types of bonds they contain and how many they contain. It's going to be tricky for some molecules because they may have double or triple bonds that you're not expecting. So follow your 5 steps as you draw out the Lewis structures. Once you have drawn those Lewis structures, you're going to add up all the bond energies for the reactants. You're going to add up all the bond energies for the products, and that's for all of the bonds. So if you have 4 of a particular type of bond, then you would have 4 times the bond energy from the table. And once you add all of them up, you're going to do reactants minus products, not the other way around. So this is different from what we do with our delta H of formation. With those, it's products minus reactants. But with our bond energies, we're going to do reactants minus products. So let's look at an example. We're trying to find the overall delta H for this reaction between hydrogen and chlorine to make 2-hydrochloric acid. So we would draw out the Lewis structures for each of the parts of the reaction. We have an HH single bond in the H2 molecule. We have a Cl-Cl single bond in the Cl2 molecule. And we have 2 HCl single bonds in the hydrochloric acid. So we're going to take the sum of the bond energies for the bonds that are broken, that is the reactants, and subtract the sum of the bond energies for the bonds that are formed, that is the products. So we'll add the bond energy for the hydrogen-hydrogen single bond, the bond energy for the chlorine-chlorine single bond together. And then we're going to subtract 2 of the HCl bond energies. Those D values you're going to look up in a table. So that would be given to you in the problem, or as you're doing your homework, you might have a big table to choose from. Just be careful as you're looking at the table to choose the correct type of bond. Single versus double versus triple have different values in the table. So the HH single bond is 436, the Cl-Cl single bond from the table is 243, and the HCl single bond is 432. So when we add 436 to 243 and then subtract 2 times 432, we get negative 185 kilojoules. Let's look at another example. We have the reaction between carbon monoxide and 2 hydrogen molecules to make methanol. So we would draw out the Lewis structure for each of those molecules. When you follow your 5 steps of drawing your Lewis structure, you find that the carbon monoxide has a triple bond between the carbon and the oxygen. And then we have 2 HH single bonds from our 2 hydrogen molecules. And then in our methanol molecule, there are going to be some CH single bonds, a CO single bond, and an OH single bond. So we're going to add up the sum of the bonds that are broken, and then we're going to subtract the sum of the bonds that are formed. So for the bonds that are broken, that's our reactants, the things on the left. So we have the CO triple bond and 2 of the HH single bonds. And then for the bonds that are formed, we have 3 CH single bonds, 1 CO single bond, and 1 OH single bond. So we would look up those values in a table and plug in the values. Again, if there are multiples of a particular type of bond, make sure you multiply it by however many bonds you have of that type. And that could be coming from a coefficient in the balanced chemical equation, or that could be coming from the fact that there are multiples of that type of bond in the molecule. So in this case, when we add all those up and do reactants minus products, we get negative 107 kilojoules. So here is a question for you to try. It's a little bit trickier because you're not trying to calculate the delta H. The delta H is actually given to you. What you're trying to find is the OF bond energy, but you're given all the other bond energies in the table. So the correct answer is A, 188 kilojoules. So you're given the overall delta H of the reaction, you're given some bond energies in a table, and you're trying to find the bond energy of the OF bond. So you would plug in all of the values for all of the bonds in the equation. There are going to be two OH single bonds, there's going to be an OO double bond, and there's going to be two HF single bonds. So you'll plug in all of those values from the table, and then for the OF2 molecule, there are going to be two OF single bonds. So when you find out sort of the missing variable, which is going to be for the OF2, you're actually going to have to divide that by 2 to find the bond energy of the single OF bond. So we've talked about the bond strength of covalent bonds. Now let's talk about the bond strength of ionic bonds. So remember, ionic compounds are made up of a three-dimensional lattice of ions. So the lattice energy is the energy that's needed to take that whole ionic compound and break it apart into individual ions. So if we had an ionic compound that had the formula Mx, it would break apart into the cation, which would be M with an N plus charge, and X would be the anion with an N minus charge. And so if we want to measure that lattice energy, it's basically just going to be Coulomb's law. We have the charges in the numerator and the distance between those charges in the denominator. And that distance is going to be the sum of the ionic radii of the positive ion and the negative ion. So the greater the charges are, the greater the bond strength is going to be, and therefore the greater the lattice energy. The smaller the charges, the smaller the bond strength, the smaller the lattice energy. With distance being in the denominator, larger radii, which corresponds to larger distance, leads to a weaker bond strength. So we can use Coulomb's law to tell us which ionic compound should have a larger energy for its lattice energy. So we have aluminum oxide and aluminum selenide, and we want to find which has a larger lattice energy. One of the things to think about is the charges. That's going to go in the numerator of Coulomb's law. So oxygen and selenium are both in group 6A, which means they both have a -2 charge. So the charges are going to be the same. The only difference between the two compounds is going to be the ionic radii and therefore the distance between the charges. The oxygen 2- ion is going to have a smaller ionic radius than the selenium 2- ion. Remember, ionic radius follows basically the same trend as atomic radius, that is larger equals lower and left, as long as you're staying within the same category of either all cations or all anions. So the oxygen ion has a smaller radius, which means it's going to have a smaller distance. And since distance is in the denominator, having a smaller distance means it's going to have a larger lattice energy. So the one with the larger lattice energy is going to be the aluminum oxide because it has a smaller distance between the ions. So we can use Hess's law to calculate lattice energy by breaking down the formation of the ionic compound into steps. We're going to use several different enthalpies in our calculation. One of those enthalpies will be the delta HF of the compound. That is the enthalpy of formation of the compound. Another one will be ionization energy of the metal. Remember, ionization energy is the energy required to remove an electron from an atom in the gas phase. Another one will be electron affinity, and that will be for the nonmetal. Remember, electron affinity is adding an electron to an atom in the gas phase. We're going to use delta HS, the enthalpy of sublimation of the metal. So sublimation is the process of going from a solid to a gas or a gas to a solid. And D, the bond dissociation energy of the nonmetal, will be another of our energies that we're going to use. So finally, we'll be able to calculate the delta H lattice, that is the lattice energy of the ionic compound. So here's a Born-Haber cycle diagram for cesium fluoride. So this is showing all the different steps that are needed to make an ionic compound or to break it apart. So we could take the cesium fluoride solid, and our first step would be basically breaking it into individual atoms. So the enthalpy of formation reaction equation would have the elements in their standard forms. So cesium would be found as a solid, and fluorine would be found as F2 gas. And then cesium fluoride would be the product. What we're actually doing here is the reverse of that enthalpy of formation reaction. We're taking that product and breaking it apart into its individual elements. So we're actually going to take the negative of the delta HF value, since we're doing the opposite of that reaction. Then our next step would be using the enthalpy of sublimation for the metal. So the metal cesium is going to go from cesium solid to cesium gas as that step. And there would be a particular energy associated with that. Then we would use our ionization energy of the metal. So the metal is losing an electron to become positively charged, and it's doing it in the gas phase. So we can use our ionization energy since the definition applies. So that particular one for cesium is going to be 375.7 kilojoules per mole. Then our next step is going to be taking the fluorine molecule, which is F2, and breaking it apart into individual atoms. So to do that, we would use the bond energy, D. But we're only going to do that as 1/2 because we have a coefficient of 1/2 in our equation. Then we're going to go from the fluorine neutral gas to the fluoride ion gas. So we're adding an electron, and it is in the gas phase. So we can use the electron affinity of fluorine, which is going to be negative 328.2 kilojoules per mole. So all of those steps added together, we have 4 of them which end up being positive and 1 of them which ends up being negative. When we add those up, we get the overall delta H for the lattice, because at that point we've reached the point where we have cesium ions and fluoride ions in the gas phase. So the overall change in that energy is going to be 756.9 kilojoules per mole, and that's our lattice energy for the cesium fluoride. So this slide basically takes what I just talked about and puts it into word form. So we have our 5 steps that are going into this. We're breaking the ionic compound into its individual elements, and to do that we use the negative of the delta HF value. The original equation has a delta HF value of negative 553.5 kilojoules per mole. But when we reverse the equation so that the cesium fluoride is being broken apart, we have to change the sign on our delta H, so it becomes a positive 553.5 kilojoules per mole. Our second step is turning the metal from a solid into a gas, so that's sublimation, and we would use the delta HS for that. Then we're going to get the single atoms of the nonmetal by breaking apart the bond. And so if we have the fluorine molecule breaking apart into 2 fluorine atoms, if we want to write our equation as 1/2 of the fluorine molecule going to 1 fluorine atom, we would have to divide our delta H by 2. So if the bond energy for the F2 molecule is 158.8, we divide that by 2 and get 79.4. Then we have the step where we turn the metal atoms into ions. So we take our cesium gas and turn it into cesium ions in the gas phase by removing an electron. And that step is using the ionization energy. And then we can turn the nonmetal atoms into ions using the electron affinity. So the fluorine is going to gain an electron, and the electron affinity applies because it's in the gas phase. So we would add up the delta H's from the manipulated equation if we needed to manipulate it, or just the original equation if we did not need to manipulate that particular step. And we end up with our 756.9 kilojoules per mole. So again, this is basically just a Hess's law problem. We just have 5 steps. And anytime that we have an ionic compound, we're going to be using these same 5 steps. The way that we apply it, the way we manipulate the equation, might change depending on the ionic compound. But the 5 steps of breaking the ionic compound into elements, turning the metal from a solid into a gas, getting the single atoms of the nonmetal, turning the metal atoms into ions, and turning the nonmetal atoms into ions will always apply. So here's a question for you to try. That's sort of a simplified version of the Born-Haber cycle. So this is just using 2 out of the 5 steps. What you're trying to do is calculate the energy change for the reaction of turning potassium and bromine into ions. And you're given ionization energy and electron affinity values for both of those atoms. And so what you have to figure out is, which one am I using ionization energy for? Which one am I using electron affinity for? And do I need to manipulate it in any way? The correct answer is A, 95 kilojoules per mole. So we're going to use the ionization energy of the metal, which is potassium, to turn it from neutral into a positive ion. And we're going to use the electron affinity of the nonmetal, that is the bromine, to turn it from neutral into a negative ion. And so we're just going to add 419 and negative 324, and that gives us 95 overall.